Okay, so we've got two lenses. We know they're 30 centimeters apart. You're looking at somebody 3 meters away. And we want to know how tall the image appears to be. I think we can treat this as a multiple lens situation. We have the original object 3 meters away from the first lens, whose focal length we know. And then that is 30 centimeters away from the second lens, whose focal length we know. So I think in this case, all we really need to do is use the first lens to find the image of the object. And then what does that image become for purposes of the second lens?
The image of one become the object two.
Yeah, so let's try that out. If we analyze lens one first, we know focal length one is 25 centimeters. And what's the object distance? How far is the person from that lens?
3 meters.
Yeah, 3 meters. We'll probably want to convert that to centimeters because everything else here is in centimeters. So let's call that 300 centimeters. And then we want to find the image distance. So how can we find the image distance here?
We use the 1 over focal equation. One focal length equal 1 over object.
Yeah, the thin lens equation. And since we're going to have to be using this twice in a row, and in both cases we're looking for the image, I would just recommend solving for image in terms of variables to get a formula for image. In this equation, before we even fill in any numbers, how would you solve for I here?
Can you repeat the question? I'm sorry.
Without even plugging in any numbers yet, if you wanted to find a formula for I, how would you isolate I in this equation?
Minus both sides for 1 over O.
Yeah, subtract 1 over O from both sides. And then what?
And then for I, we can just take the 1 over whatever on the right.
Yes, although to make things easier, it's a lot easier to invert this if we have just one big fraction. So how would you combine these into one fraction first?
Times, well, one we times O, the other one we times F.
Yeah, if we multiply the first one by O over O, we get O over O times F. And then multiply the second one by F over F, we get F over O times F. Now we at least have the same denominator. So combining those, 1 over I equals, combining the numerators, O minus F over O times F. And now we can just invert both sides. I over 1, that is just I, equals the inverse, O times F over O minus F. So we can use this as a general formula for the image. The image distance will be object distance times focal length over object distance minus focal length, product over difference. Any questions on that so far?
No.
So now instead of solving this equation over and over again, we can just use this version of the equation to directly find image. So O times F, that'll be 25 times 300. And since all of the distances are in the same units, we can assume those will work out nicely. We're going to end up with centimeters times centimeters divided by centimeters. So that'll just be centimeters. So 25 times 300 divided by 25 minus 300, which is going to be negative 275. And without multiplying that all out, does anything reduce here?
I don't know. I just put the whole thing in the calculator.
Well, I guess you could do that also. Sorry. I think you can make it a lot simpler by noticing that 275 is a multiple of 25. So you could reduce those. But either way, what does that work out to?
I equal 27.3.
Sorry, what was it?
27.3.
Yeah, and that should be a negative also, so negative 27.3. That'll be the image distance. And I think that since that's going to be, that's pretty close to the 30 centimeter distance apart. So I think oh wait, it's negative though. So where does that image actually show up?
Um, how come it's negative again? O
What's O minus F?
O
Oh,
minus
I got
F
those backwards,
is,
didn't I? That should be positive.
yeah, 300. Yeah. So it
Yeah,
should be plus 27.3.
yeah, positive 27.3, which means where is the image?
Well, because it's the lens, is it a lens? Yeah, it's a lens
Mhm.
and it's a positive image, meaning that it's real image.
Yeah,
And in real image of the lens is opposite side of the objects.
yeah, because the light's going through and we treat the direction light is traveling as the positive direction. So that means the image is going to be over here,
Mhm.
specifically 27.3 centimeters from the lens itself.
Can I ask you a question? So
Mhm.
from I, if it's plus or minus, can we conclude that if it's plus, then it's real image, and if it's minus, then is virtual image?
Yeah. Yeah, the image distance positive always means for I, the image that for the image distance I, a positive value always means in the direction light is traveling at the end. And the side of the lens or mirror where light is traveling is going to be the side where you would expect a real image. Whereas if I happens to be a negative value, that means the image appears on the side of the lens or mirror that light is not traveling on, which means it would have to be a virtual image.
And then the real image is always right side up.
Other way around, should be upside down.
So real image is upside down.
Because if you were to draw out the optical axis here and draw out a principal ray, specifically the easiest principal ray to draw would be the one that's going from the top of the object through the center of the lens and just keeps going. So that means the image of the guy's head is going to be below the axis. The guy's head was above the axis. The image of his head is going to be below the axis. So the image will be upside down.
Yeah. Is it upside down relatively to the object always, right?
Yeah, it's always relative
Like if
to the object, or in a multiple lens setup, relative to the previous image,
yes, okay.
not necessarily to the original object.
Mhm, mhm.
And then how would we find the distance, since we're treating that image as the object for the second lens, how would we find the distance from there to the second lens?
We have the distance between the two lenses are 30
Mhm.
centimeters apart. So D equal object 2 plus image 1.
Mm-hmm. So how far would that distance be?
So 30 minus 27.3, 2.7. 2.7.
Yeah. So 2.7 centimeters. That'll be our new object distance. So for lens 2, we can say F2 is negative 5 centimeters. It's a diverging lens. O2 is that 2.7 centimeter distance. And then we can use the thin lens equation again to solve for image 2. So that'll be, again, image is O times F divided by O minus F. So filling in
So
the thumbs. Mm-hmm.
I have negative 1.8.
Okay. Yeah, that should do it. About negative 1.8.
So after we calculated the image two, the question asks us is the image is upright or inverted. If it's negative, meaning that it's negative image mean virtual image, so it's right side up with the objects. Right side up with the object two, meaning that is upside down with the original object one.
Right. And we can also figure out the size based on the magnification factors. If we calculate the magnification factor for each one, like how would we calculate the magnification factor for lens one?
That's gonna be negative I1 over O1 equal H1 over, HI over HO.
Yes, although we don't really need to worry about the image and object yet, the heights yet. I think we can just find the magnification from I1 and O1. So magnification I1 over O1 is going to be what fraction or what decimal?
Negative 0.091, or do you want ratio? Oh,
that should work. I mean, that we can treat that is a fraction. It's just 91 over 1,000. So that means that the image one is going to be 91 1,000ths of the guy's actual height and upside down because of the negative sign. What about image or magnification factor two?
Negative 0.67.
Is that negative? We got a negative image and also a negative formula.
So it's a positive.
Yeah. So that means that the second image is going to be 2/3 as big as as its object, the first image. And also positive means same orientation. And how would we combine these to get the total magnification?
Multiplication.
Yeah. Magnification factor is a multiplier, so we combine them by multiplying. And what do you get there?
Negative 0.06.
Yeah, that sounds about right. So that means the final image, because this is for the entire system, the final image will be 0.06 times as big as the original object and upside down compared to the original object because of the negative. So we can multiply 0.06 times the guy's height to get the height of the final image. Any questions on that so far?
No, I just got mixed up between the inverted and the right side up, but it's clear. Thank you.
Yeah, the first lens flips them upside down. The second lens makes no further change. So the final image is upside down compared to the original object.
Can you explain how come sometimes that the D, we have to, like, I always remember the D is object 2 plus image 1. But sometimes it's a negative sign instead. Can you?
No, that equation should always work. O2 plus I1 should always equal the distance between the lenses.
Oh, okay. Because I remember there is like one quiz that we have to take the negative of it. Do we still have time? Do you want to?
Sorry, what was that? I couldn't hear you.
Because I remember there was one quiz that we have to take the negative sign.
I don't think so. I think I1 plus O2 should always equal the distance between lenses. That should work even if I1 happens to be negative or O2 happens to be negative.
Okay.
The geometry gets a little weird, but algebraically, this equation should still work either way. Gotcha. It turns out it even works if I1 is a positive number that's bigger than the distance between lenses. you end up with a negative value for O2, which leads to some rather weird results, but it still gets you the correct answer. You would just treat O2 as a negative number in the equation. And it certainly makes the ray tracing really difficult to draw out because the first image doesn't actually resolve since it's on the wrong side of the second lens. And we would call that a virtual object. But algebraically, it still works fine.
Got it. Thank you.
Mm-hmm. And did you say you wanted to work on a couple of the problems on the other practice final as well?
Yes. Can we go through, can we skip? I think I said number 3 and number 6. Can you scroll through if I got it right? I don't, because I'm not sure where.
Which one did you want to take a look at? I think number 6 was the one with the magnetic induction stuff.
Oh. Let's do number 3 actually.
3 was, I think that was more lens stuff. What was that?
Yeah, but with the plus 2D one.
Mm-hmm.
So I'm not sure what that is.
Oh, D is diopters. Optical power is if you go back to the thin lens equation, the 1 over F equals 1 over O plus 1 over I. In physics, we generally talk about lenses in terms of their focal length, measured in centimeters. But in optics, like in terms of actually making corrective lenses and telescopes and stuff, opticians often talk about lenses in terms of what's called the optical power. And optical power is just a name for the 1 over F fraction. So optical power is just 1 over F, 1 over the focal length.
Meaning
so when we say the optical, sorry, what was that?
Sorry. So meaning in this case, 1 over F is equal to plus 2D.
Yeah. And the diopters is that 1 over meters or 1 over centimeters? I think it's 1 over meters. Yeah, 1 over meters. So diopter just means inverse meters. So if the optical power is 2 diopters, you just invert that and convert 1 over diopters to meters. So optical power equals plus 2 diopters means that the focal length, or we could even write this as 1 over the focal length equals positive 2, 1 over meters. So if you invert both sides of that, inverse of positive 2 is positive 1/2, and inverse of 1 over meters is meters. So the focal length is half a meter, or 50 centimeters if you'd like to write it in centimeters.
Gotcha. Thank you. So I guess we can do number 6 if we have time, but I don't think we can.
Sorry, what was that?
So I think we can do number 6 if we had time, but I don't think we can because I'm just confused about the 2D part. I think the rest is just just thin lens.
Yeah, diopters just means 1 over meters, and the optical power is 1 over the focal length. So if you just take the optical power, invert it, and then change 1 over diopters to meters, that's your focal length in meters. So yeah, let's take a look at the number 6, you said?
Yes, number 6.
Okay, so here we've got a couple of resistors. And then we've got this metal bar that's moving through a magnetic field. And why would that create current in the first place?
Because there's change in flux.
Yeah, moving the bar causes a change in flux. And this actually causes, there's really 2 magnetic flux values that we're keeping track of here. Because this bar creates 2 loops. We've got this loop of wire, if we treat the bar as making this connection. This loop of wire, which has enclosed this area, which encloses some of the magnetic field. And then we've also got this loop of wire, which encloses this region with magnetic field. And if we move the bar, like let's say we move the bar 1 meter to the right, that's going to shrink this loop and expand this loop. So that means the flux on the right loop is getting weaker, the flux in the left loop is getting stronger. So both fluxes are changing, which means that both of these loops get an induced voltage. Any questions on that so far?
No, from me.
And I think we can figure out the, if we take a look at the rate of change here, because ultimately what we care about is the derivative of flux. And how do we define flux in the first place?
The magnitude going through the loop.
Yeah, how much of it is going through the loop? And how do we actually calculate that?
AB cosine theta.
Right. Area times magnetic field times cosine of the angle with the normal line. In this case, what's the angle between the magnetic field and the normal line?
We can take the normal line going out of the page, so the theta is 0, so cosine theta is 1.
Yeah. So we can say flux is just area times magnetic field. And the magnetic field is constant. That's just a constant 50 Teslas. But it looks like the areas are changing. One of them is area is growing, the other one area is shrinking. But let's take a look at this in terms of absolute value for now. Ignoring whether the area is growing versus shrinking, can we figure out how fast the area is changing?
Yes, because we were given the speed of changing.
Right. And area, since this is a rectangle, how do you calculate the area of a rectangle?
Length times width.
Yeah, length times width. Let's call that, let's say y times x. And as the bar moves, the rectangle is changing its area. Of the y value and the x value, the height and the width, which one is actually changing?
The width is changing.
Yeah. So x is changing, but y is constant, 2 meters. So the y value, the height here is always 2 meters, but the x is changing. So if we take the derivative here, y is constant, so it can be pulled out of the derivative. We just get y times dx dt. But what do you call dx dt? What's the derivative of position or distance?
I'm not sure. I'm not sure about the calculus size, sorry.
Think back to 7b. What do we call how fast the position is changing or how fast the distance is changing?
Oh, it does. Is that speed?
Yeah, that's just v, the speed. And you can also see this in terms of units of measurement. Distance is measured in meters, time is measured in seconds, so we get meters per second. That suggests speed, because that's the units of measurement for speed. So dA dt, the derivative of area, that is how fast the area is changing, is the height times the speed the bar is moving. And we know those values. We know the height is 2 meters. We know the speed is, do we have the speed?
Yeah, 0.2 meter per second.
Yeah, so 0.2 meters per second. Multiply those, we get 0.4. And what are the units we get there if we combine those?
Meter squared per second.
Right, meters squared per second. So that tells us how fast the area is changing. The area is changing by 0.4 square meters every second. So that's dA dt. That's the rate of change of the velocity. Or sorry, rate of change of the area. And that's for both of them. One of them is growing by 0.4 square meters per second. The other one is shrinking by 0.4 square meters per second. But the absolute value of the rate of change is the same for both. And for flux, what we really care about is the rate of change in flux. Induced voltage equals the rate of change in flux, how fast the flux is changing per unit of time. And formally, there's a negative in there also, which just represents the direction. But if we just care how much voltage, we can ignore that negative. So absolute value of induced voltage, usually written as epsilon. You can just copy from here. No, they're just using a font. Epsilon, where is it? There. So the induced voltage is going to be just d flux dt. That is the amount of voltage. I guess that should be an absolute value also. So the amount of voltage we get is just the absolute value of rate of change in flux. And since if we take the derivative of flux, that is derivative of A times B, we know B is constant, so we can pull that out of the derivative. So we just get dA dt times that constant magnetic field. Since magnetic field is constant, we can pull that out of the derivative. And we know the derivative of area, that's 0.4 square meters per second. We know the magnetic field, that's 50 teslas. So we should be able to just multiply those together. Rate of change in area, 0.4 square meters per second. Magnetic field, 50 teslas. Multiply those and what do you get?
20.
So that is 20. And if you combine teslas, meters squared, and divided by seconds, that ends up being volts. So that means the induced voltage is 20 volts here. Each one of these loops is going to experience an extra voltage of 20 volts, exactly as if there were some sort of invisible 20-volt battery. It's not coming from an invisible battery, of course. It's coming from the fact that the magnetic field is the magnetic flux is changing. But that changing flux acts like an extra plus 20 volts from a battery, which means current's going to flow. And how would you calculate how much current?
Ohm's law.
Yeah, the voltage on the resistor is current times resistance. We know the voltage is 20 volts for both loops. Each loop individually gets 20 volts. So we can just divide by each resistance to find the current through that loop.
Gotcha.
So that'll be what, 20 over 20 and 20 over 30. So 1 amp and 2/3 of an amp will be the current through the two resistors. And how would we figure out direction current is flowing?
Right. So, so for the left loop, because the magnetic fields, it's going out of the page, and it's increasing as the area change, meaning that the direction of the change of the flux is also out of the page.
Right.
Meaning the induced voltage is the opposite direction of that. And then
right. The induced effect is going to be in a direction opposite to the change.
And then we use the right-hand rule, number 1, to figure out so it's inside, so the I should be clockwise or the left.
Sorry, what was that?
And then we use the right-hand rules, number 1. So the I should be clockwise for the left loop.
Yeah, that should work. And then for the right loop, we should just expect the exact opposite result. So it looks like that's going to be, yeah, clockwise for the left loop, and then counterclockwise for the right loop. Notice though that this bar in the middle, both of those currents end up having current going down. So those are going to combine and we're going to end up with a very strong downwards current through the bar.
Meaning that in these kind of problem if like our result is like not agree with each other between the two loops, that we might be wrong, right? It
I don't
has
know. I
to.
think it depends on the circumstances. Like in this case, we end up with clockwise in one and counterclockwise in the other because we're shrinking one loop and growing the other loop.
Okay.
But
But
if we were
like,
doing something that, let's say we take this double loop and we stretch it out, like if we stretch out the end, so we're expanding both loops, then I think that would cause current to flow in the same direction in both loops.
gotcha. Okay.
Which I guess would mean that in the middle, if there's a bar in the middle, that would end up with current going in opposite directions and partially or completely canceling out.
Mm.
But all the junction rule stuff from 7b still applies. You can just take the current going in from this side and the current going in from this side and add them to get the current going out through the middle. Any other questions on that?
No, thank you.
Or anything else you'd like to work on?
Wait, how long can you stay?
I'm here for about another 10 minutes.
Oh, nice. Okay. Can we work on? Oh, there it is. Huh. No, which practice? Maybe number. Let me drop this.
Which one?
Sorry. Let me drop the files in thing for you because it's in another one.
So what's going on in this one?
So quantum mechanics problem, and then it's mentioned hydrogen. So I'm assuming it's a 3D box hydrogen-like atom.
Yeah, I think we can use that as the usual formula. The thing is, though, I don't think we really need to use that formula for the energy levels because it's not asking what levels or which energy levels are these. It's just asking for a difference in energy based on the light that it produces. So we've got, and it's producing radio waves. So presumably it's starting at a high level of energy and dropping down to a lower level of energy. So if we looked at this on the usual charts we've been making, just like an energy axis, we're starting at some high energy and dropping to some lower energy level. We don't even know which energy levels they are in terms of like end value. But we do know that as we drop from one energy level down to the next, this is some unknown delta energy. And we don't know how much energy that is, but we do know that as it drops from this level to this level, it's emitting a radio wave with wavelength 21 centimeters. So I think that's the key here. We can use that wavelength to figure out how much the energy difference is. Wavelength 21 centimeters. And if we know the wavelength, how can we figure out what energy corresponds to that wavelength?
Well, so dropping from the higher level to the lower one, it's emitting like a photon.
Sorry, what was that?
So when it's dropping from higher level to the lower one, the delta energy is equal to the photon is emitting. So it should be equal to the energy of the photon, which is hc over wavelength.
Yeah. So that means, and since we know the wavelength, if we just take h times c, Planck's constant times speed of light, divided by the wavelength, that'll tell us the energy of one photon, which is the energy that the system loses as it drops from this level to this level. So I think that's all we really need to do here. Find the energy of that one photon that corresponds to a 21 centimeter wavelength. And that'll tell us how much energy the system loses. And what value could we use for h times c here?
See, that's what I'm confused about. Because like I want to use the 1240 EV times nanometers. So I want to change yeah. I know, so I have to convert the wavelength into nanometers.
Yes, although we could just think of it in terms of what centa means and what nano means. Because meters and meters are going to cancel out anyway.
Yes.
You could just look at this as meters and meters cancel out. So we end up with 1240 over 21 electron volts times nano divided by centi. What do nano and centi mean? Like
centi
when we say
is like
centi,
100, right?
What was that?
Centi is like 100
So
from
the
meters.
centimeter mean 100 meters?
No, 0.01 meters.
Yeah, 1/100th of a meter. And it's going to be useful, I think, to write these as powers of 10. 0.01 or 1/100th is 10 to what power?
0.01 is 10 to power -2.
What was that?
-2.
Yeah, centi just means 10 to the -2. And what about nano? That's 10 to the what?
Either 6 or 9. I don't remember.
Yeah, I think it's 10 to the -9. 1 billion, is that right? Just nano would be billion. Let me double check that. I think it's 10 to the -9. Yeah, 10 to the -6 is micro. So nano is 10 to the -6. -6 is micro. Okay. -9 is nano.
Gotcha. Okay.
So yeah, 10 to the -9 is nanometer, nano anything. 10 to the -2 is centi anything. So if we just divide 10 to the -9 divided by 10 to the -2, what would we do with those exponents?
Minus them?
Yeah, we can just subtract the exponents. -9 minus -2, that's the same as plus +2. -9 plus 2 is -7. So 1240 over 21 electron volts times 10 to the -7. So 1240 over 21, what's that going to be? 59. So 59 times 10 to the -7 electron volts. So that would be the difference in energy between those two levels. It's an energy gap of 59 times 10 to the -7 electron volts.
Gotcha.
Any other questions on that?
No, not on this.
All right. Or any other quick questions before I go?
There is actually one quick question that I have. So I'm usually confused with the Doppler effect and also the beats.
With what?
Doppler effects and beats. So like through a lot of like exercises, I think usually that so like if the two sources, we have to have at least sources to create beats, right?
Yeah.
So if the two sources is like being turned on together at the same time. So that can recreate beats. And then the frequency, that's the beat frequency, which is take one to subtract the other. And then the frequency that we hear, they call it carrier frequency.
Mm-hmm.
And then whenever we move that source, then we have to consider what Doppler effects due to those source first, and then we consider what the beats that those two sources created, and then also the F carrier.
Yeah, because
right?
when we talk about the difference in frequencies and the average of frequencies, the frequencies we're talking about are the two frequencies you're actually receiving. Those won't necessarily be the same as the frequencies the sources are actually producing, because those frequencies might be modified by the Doppler effect if the sources are moving. But keep in mind that the Doppler effect and beats have nothing to do with each other than that they both involve waves. The only reason they often get combined in problems is that they're both introduced in the same time in the curriculum. But it's entirely possible that, in fact, very common to have beats without a Doppler effect, and very common to have Doppler effect that has nothing to do with beats. Doppler effect happens when the source of the sound or the listener are moving, or both. And beats happen when you've got sounds or any wave with slightly different frequencies.
Okay. But then if they combine the two problems together, like, would it be like the safest way to get the right answers? Like, you see what the Doppler effect does to those two sources, and then you just combine them as beats.
Yeah, all the frequencies being described in terms of beats, like the frequencies we're taking the difference of, the frequencies we're taking the average of. The two frequencies are the two frequencies that the listener is actually observing.
Mm-hmm.
So you use, because we're talking about the phenomenon that the observer observes. So you would use the frequencies that the observer actually receives, not necessarily the frequencies that the sources produce.
And then also, sorry, one more thing, just one last thing. So when they say that as you move from, like, for example, when they say that you move from the side that that there's destructive interference between the sources, and then you move to the first constructive interference, does that means that at that point is the total phase different? Is that, how do you call it?
Mm-hmm.
Is that 0 or is it 2 pi?
It could be either one. It could be 0 or 2 pi or 4 pi or 6 pi, any even numbered multiple of pi. That is any whole number of cycles.
So it doesn't matter. You can just assume that you can just assign any even number, and then you can just solve for the same they should have the same result.
Yeah, but keep in mind, you've got to be consistent about it. Like if you have a destructive location that you're calling, let's say this destructive location is labeled phase difference equals 3 pi. If you then move to the very next constructive interference, you can't call that one 8 pi, because 3 pi and 8 pi are not close to each other. If this destructive location is labeled 3 pi, the very next constructive location would be either 4 pi or 2 pi, depending on the direction you're subtracting. So they've got to be the very next even multiple of pi or the very next odd multiple of pi.
Gotcha. Okay. Thank you, Casey. Thank you
welcome.
for staying extra time.
Yeah, glad I could help. Good luck on finals. See you next time.